Cool. Hi, everybody. Welcome back. Thanks for joining us again. Here we are at our Wednesday High Energy Phenomena Seminar. So today we have two wonderful speakers lined up. Without further ado, let's get started. Oh, actually, one thing I want to mention for people who may have just gotten here, if you hear this noise in the middle, don't worry about it. As we let our speakers know, we will be ringing that at the 3-minute mark because nowadays we can't hold up placards very effectively. So, all right. Our first speaker is Dr. Arya Farahi. Arya received his PhD in physics and scientific computing, sorry, getting tongue-tied, scientific computing from the University of Michigan in 2018. After that, he spent a year at Carnegie Mellon University as a McWilliams postdoctoral fellow, and then came back and rejoined the University of Michigan as a data science fellow with the Michigan Institute for Data Science. His main research interest ranges from galaxy evolution physics to alternative probes of cosmological parameters, but he's also interested in developing novel analysis tools and theoretical aspects of statistical inference and algorithms. Currently, he's the co-chair of the Baryon-Pasters collaboration that develops novel computational tools to facilitate modeling and analyzing astronomical surveys. He also recently co-founded the Michigan Data-Informed Cities for Everyone. This is an organization that partners with cities and local governments to help them deploy data-driven and AI solutions, because we all know we need more data going into our communities. So without further ado, Dr. Arya Farahi.
Yeah, thank you so much, Ritu, for the kind introduction. Can you hear me?
Mm-hmm.
Yeah. All right. So before jumping to my talk, I was also talking to Ritu, and my research was mostly like astronomy when I was a PhD student. Now my research is shifting toward application of data science, machine learning tools, and novel statistical tools to applications in astronomy and cosmology. And I'm developing a lot of open source and new softwares for the astronomy community. So I'm going to talk about one of these softwares that we developed and released this past summer. But if you have any questions, I'm always happy to talk about them. And if you have any challenges and wanted to develop a new software or theoretical models or data analysis models, I'm always happy to learn about and new challenges in astronomy, and I'm trying to develop problem-specific models. All right, so Pope is mostly motivated by the fact that galaxy clusters are a good probe of the cosmological parameters. So we know that if we can go to our universe, find the location of the dark matter halos, measure the mass of these dark matter halos, then we can constrain the cosmological parameters pretty well. But unfortunately, we know that the mass of these dark matter halos is not directly observable to us. So we have to rely on the luminous matter, which is sitting inside these dark matter halos, and use them as a proxy for the mass of their host. But observation, it is even more challenging. We have to develop a cluster finder algorithm in the first place based on which type of data set that we are working with. Then we have to measure some of the observable properties of these galaxy clusters, and then probabilistically map these observables to the mass of the host dark matter halos. So essentially, we have these two-step model. We start from the initial condition and the cosmological parameter of the universe. Then we can specify the number density of the dark matter halos and how they evolve as a function of redshift. And in the next step, we have the mass observable scaling relation, in which we are trying to build this probabilistic model, which goes from the mass all the way down to the observable. In this talk, I wanted to advocate for the fact that we need one extra step that is related to the galaxy formation and the gas physics. And it is going to explain some of the scatter that we are seeing the mass observable scaling relation. And eventually down the road, it is going to help us to constrain the cosmological parameters better. So ideally, in terms of cosmology, we wanted to identify one cluster observable, which can be uniquely mapped to the mass of the host dark matter halo. But in practice, we know such observable does not exist. Most of the time, the observables are scaling as a function of the mass of the host dark matter halo, but we get a huge amount of scatter about this mean relation. So we have to both quantify this mean relation and how much scatter we have for each observable. So this scatter is a little bit annoying for people who are doing cosmology, but as I'm going to argue, this scatter has a lot of information in it, which we can use to constrain the astrophysics. Or if we know the astrophysics, we can use it as a prior and constrain how much scatter we have. So essentially, we have to add this second layer into our model. We have to specify the galaxy formation physics and gas physics, and it is going to help us to construct a better halo mass proxies based on the observables that we have. So this talk is going to be mostly focused on the second part, how we can incorporate this information and how we can explain the scatter in the mass observable scaling relation. I'm not going to talk about cosmology at all. So let's take formation time as one example. So imagine that we have two dark matter halos of exactly the same mass, and initially we are going to populate them with exactly the same number of galaxies. But one of these dark matter halos form at the early redshift and the other dark matter halo form at the late redshift. So as time is passing and they are reaching to redshift 0, the galaxies inside the early form dark matter halos had enough time to go through dynamical friction, lose their kinetic energy, and merge into the central galaxy. But the satellite galaxy inside the late form dark matter halo, they didn't have enough time to merge into the central galaxy. So this model predicts that the mass of the central galaxy should be larger for the early form dark matter halos compared to the average population. And we expect to see smaller number of satellite galaxies. So you see that this model is automatically producing some scatter in the mass observable scaling relation, because we started with exactly the same mass, but at redshift 0, we have a different number of satellite galaxies. So this is the hypothesis that we wanted to test, to see whether the formation time is correlated with the scatter or not. But unfortunately, the formation time is not directly observable to us. We have to rely on the proxies of the formation time. And most of the proxies that proposed in the literature are very hard to measure, or if we can measure them, they are going to be very noisy measurements. But fortunately, there is one single observable that is tightly correlated with the formation time, and it can be very easily observed, and that is the magnitude gap. So essentially, I have two hypotheses that I wanted to test. One is whether the formation time is correlated with the magnitude gap, and the other one is whether the formation time is correlated with the scatter in the mass observable scaling relation or not. So to test this hypothesis, we are going to take the output of TNG 300 simulations and test this hypothesis. Because I'm mostly interested in the most massive halos in our universe, which correspond to the galaxy clusters we have in our observational data, I took all of the halos above 10 to the power of 14 solar masses at redshift 0, measured their formation time, their magnitude gap, which is the R-band magnitude difference between the brightest and the second brightest galaxy. And here I have the formation time as a function of the magnitude gap. So you can see that there is a tight correlation between these two quantities. Early form dark matter halos correspond to the high magnitude gap population. And late form dark matter halos correspond to the low magnitude gap population. So indeed, we can use magnitude gap to probe the formation time. And now we can ask how the magnitude gap is correlated with the scatter of the mass observable scaling relation. All right, so here I have the number of satellite galaxies as a function of halo mass. And this is color coded according to the magnitude gap of this system. So as expected from our model, the number of satellite galaxies for the late form dark matter halos or a low magnitude gap population is much larger than early form dark matter halos or the red population. So this is completely consistent with our model. So now let's look at the stellar mass of the BCGs. We saw exactly the opposite trend for the stellar mass of the BCGs. Early form dark matter halos has a more massive BCGs. So it means that these BCGs are growing by merging of the satellite galaxies. And so, all right, but one very interesting observation is that if we can condition on the magnitude gap of this system, we can explain 60% of the scatter. That is super exciting because it means that if we incorporate this information to our mass observable scaling relation, then we can explain some of the scatter and we can construct a better halo mass proxy. And down the road, it is going to help us to reconstruct the halo masses better and reconstruct the cosmological parameters better. All right, but now the key question is that whether it is consistent with the observational data or not. So Golden, Marks, and Miller in 2019, they took an optically detected cluster sample. They measured their stellar mass of the BCGs as a function of the mass of the dark matter halos. And this is again color-coded according to the magnitude gap. And they saw that the high magnitude gap population has a more massive BCGs. I did go to a group sample identified by the Temple et al. From, again, SDSS sample, did the same exercise and found exactly the same thing. Here I'm using the velocity dispersion as a proxy for the mass of the host dark matter halo. And again, for this sample, the high magnitude gap population correspond to the more massive BCGs. So what we have seen in the simulation is consistent with our theoretical model, and it is consistent with what we are seeing in the observational data. But now I wanted to talk about the correlation. This is the key quantity that I'm going to look at in the rest of this talk. So if we assume that this scatter is induced by some astrophysical phenomena or galaxy formation physics, in this case, if it is induced by the formation time, if we look at two different halo properties, whether they are correlated or anti-correlated with the formation time, automatically it is going to induce correlation or anti-correlation in the scatter of two different observables. So really we can go to our scaling relation, measure the scatter, and measure the correlation coefficient between the scatter of two different observables. I did go to the TNG 100 simulations, measure this correlation coefficient for a number of optically observables of these galaxy clusters. So now we quantified this effect from the TNG simulation, and now we can go to the observational data, measure this correlation coefficient, and see whether the value we are getting from the simulated data is in agreement with what we are seeing in the observational data or not. So we can do exactly the same exercise on the X-ray observables as well. For example, we can look at the X-ray luminosity and the gas mass, perform a scaling relation, measure the scatter, and measure the correlation between the scatter of these two quantities. So people have done this in the past in a multiple different hydrodynamical simulations. So now we took this data, we took some observational data, which is coming from the locus sample, which is an F41 galaxy clusters identified from an X-ray survey. And then we collected multi-wavelength data, performed the scaling relation, and reconstructed this correlation coefficient. So the blue shaded region is the posterior distribution we got from the observational data. And as you see, the posterior distributions are in agreement with what we are seeing in the simulations. So this is especially very exciting for people who are performing these numerical simulations, because it was not, these simulations are not tuned to reproduce these observables. We did go to the observational data, measure this correlation coefficient, and saw that they are in a great agreement with the simulated data. All right. So now let's change the gear a little bit. So far I was fixing the scale of the dark matter halo, and I was asking what is the correlation coefficient between the R200 of the dark matter halos. But we expect that this correlation coefficient and how much scatter we have be a function of the scale that we are looking at. For example, if we go to the core of the dark matter halo, then the AGN feedback, the supernova feedback are becoming more important. They are producing more scatter, and they are changing the value of this correlation coefficient. But when we are going to the outer skirt of the dark matter halo, everything should be driven by the gravity. So all the correlation coefficient should be sensitive to our gravitational model. So basically, by probing how these correlation coefficients and scatter are changing as a function of the scale, we can get a better information about what is happening inside these dark matter halos. All right, so this has motivated us to go to the, again, simulated data, measure the value of the scatter at different scale, measure the value of correlation coefficient, and see what we can learn from it. So the idea was going beyond the bulk properties of the dark matter halo and start looking at the profile properties of the dark matter halos. So in this work, we started to look at the density profile of the dark matter particles, density profile of the star particles, and the density profile of the gas particles. So each line corresponds to the average density profile as a function of the halo mass, and each data point corresponds to measurement coming from one single dark matter halo. So you see that there's a huge amount of scatter, especially if we are looking at the stellar and the gas density profile. So the natural question would be how much they are correlated with each other and how these correlation coefficients are changing as a function of scale and as a function of the mass of the host dark matter halos. So here I'm showing you the result of the correlation analysis. So here I have the correlation coefficient between the dark matter and gas density profiles as a function of the distance from the core of the dark matter halo and as a function of mass of the dark matter halo. The same thing for the dark matter density profile and the stars density profile, and stars and the gas density profiles. So one interesting observation is that if we go to the outer skirt of the dark matter halos, beyond R200, because everything is gravitationally coupled to each other, we expect to see a strong positive correlation between all phases of matter. And this is exactly what we are seeing in the simulations. But as soon as we go to the core of the dark matter halo, we see a completely different picture. This correlation coefficient starts to vanish. We think that this is happening because of the feedback mechanisms, especially if we look at the AGN feedback or supernova feedback. They are going to heat up the gas, evacuate the gas from the core of the dark matter halo, and as a result, dark matter particles and gas particles become gravitationally decoupled. Once they are gravitationally decoupled, this correlation coefficient vanishes. So basically, by probing at which scale this correlation coefficient vanishes, we can gain some information about the power of these feedback mechanisms. All right, so now let's say that we have a theoretical model which is going to make prediction about these correlation coefficients and how they are changing as a function of a scale. But the key question is that, are they going to be observationally detectable, or this is just a theoretical model? So there are a lot of challenges of working with observational data, especially with the ongoing data and future data. We are not going to have a very high signal to noise measurement, especially if we are looking at the density profile of a lot of dark matter halos. Typically, to increase the signal to noise ratio of the measurements, we are performing a stacking analysis. We are stacking the signals on top of each other. But unfortunately, stacking is not an option for this exercise because it is going to suppress the scatter and especially the correlation signal that we wanted to measure. So we have to really develop a population-based method to infer the variance and the correlation between two properties from the low signal to noise measurements, even below the detection threshold. And ideally, we wanted to have a non-parametric model. We don't want to make an assumption about the shape of these density profiles and how they are changing as a function of mass or other observables. So to address this challenge, we develop our own data analysis pipeline, which we call it POP. POP is standing for Population Property Estimator. It is a Bayesian inference method that takes low signal to noise measurement and output the value of the correlation coefficient and reconstruct these average profiles. The code is publicly available. You can download the code and play the code and even run the code on your data. And I'm more than happy to sit down with you or help you to set up the code and even run the code on your data. So now let's talk about how the model is working and showing some results from this model. So basically, the first part of the model is reconstructing the average profile as a function of different observables, let's say mass and the redshift of the dark matter halos. And in the second part, we are reconstructing the covariance between different observables. And this covariance consists of the scatter and how much correlation we have. All right, so but we have to prove that this model is working in a low signal to noise regime. So I start with the toy model. in my toy model, I have two density profiles which are exponentially decaying. I add some intrinsic scatter with some assumed correlation between the scatter of these two quantities. I add the measurement noise. And here on the right, I have the signal to noise ratio of the measurement. So indeed, we are working with the low signal to noise regime. So now the question is that, can we reconstruct this average profile and the correlation with this low signal to noise measurement? And the answer is yes. So here it is showing the posterior distribution we are getting from this low signal to noise measurement for both of these density profiles. And here I have the input correlation coefficient versus the inferred correlation coefficient. So indeed, we can reconstruct this correlation coefficient almost perfectly. So let's do the same exercise on the TNG data. So with TNG data, again, we start with the intrinsic properties, add the measurement noise. Here on the right-hand side, I have this signal to noise ratio distribution of the measurements. We pass this noisy measurement to probe. And here, this is the reconstructed posterior distribution for the average profile as a function of mass. And it is completely consistent with what we expected to get. All right, so now the last and the key question: can we detect it with our ongoing cluster samples? So it turns out that the answer is that no, if we have around few hundreds of dark matter halo. So the constraints that we are getting is these dots. Basically, they are scattered around zero with a huge error bar. So basically, we cannot reconstruct this correlation coefficient if we have around few hundred dark matter halos or galaxy clusters in our sample. But as soon as we have around few thousands or tens of thousands of dark matter halos, then we are able to reconstruct this correlation coefficient from our observational data. And we know that with ongoing data and with future deep array data, we are going to have around tens of thousands of galaxy clusters. So essentially, with ongoing data and future data, we are able to reconstruct this correlation coefficient. Now we have to think how we can use this information to constrain astrophysics happening inside the dark matter halos. All right, so I'm going to leave you with my conclusion. So I hope that I convinced you that the scatter is actually not that annoying. We can use the information existing in the scatter to constrain the evolution and dynamics of these systems. And the future is not going to be about one single scale. We have to look at the properties of this dark matter halo as different scale, and it is going to give us a huge amount of information to constrain the physical processes and the gravitational model, which are controlling the evolution and dynamics of this system. And now we have the tools to apply it to our observational data and constrain these parameters. Thank you so much for your attention, and I'm happy to take your questions. Thank you.
Thank you, Arya. If anybody has questions, you can raise your hand in the participant thing. You can put it in the chat or on the Slack channel. We already have one question, so Mila, go ahead.
Hi, thank you. This is really interesting. I have a few questions.
Sure.
So the most basic one is, how sensitive is this to your training sample? So like, this is essentially, does this assume that the TNG galaxy formation model is correct? Have you tried training it with other comparable simulations, and does that give you different results?
Actually, this is not a machine learning model. So we are not training the model on any simulation. We are relying on the observational data and reconstruct these density profiles from our observational data. So we are not incorporating any prior, or we are not assuming any shape for these density profiles, which are trained from our numerical simulation. We are just relying on the data to reconstruct these density profiles. For example, in our toy model, this toy model is not motivated by any density profile that exists inside TNG simulation. This is something I came up with, and I added the measurement noise completely randomly. So this is not corresponding to anything that we have in the TNG simulated data. It was a very good question, and probably I was not very clear, but it was not a machine learning model. It was mostly a statistical model, and we were making as a very, very minimal assumption about the shape of these density profiles. Basically, we are making assumption that they are smooth. That's it. We are not making more assumption. And we are making assumption that the scatter is following a log normal distribution. So if we have a skewed distribution, then this model is not going to work. But as long as these assumptions hold, then we should be able to reconstruct any density profile from observational data.
So on the slide that you were just on, those red points are those observations?
Here, red points are actually from the TNG data. So this is just for illustration, but here, this is what construct our observations. So our observations are each individual data point measurement for the density profiles and their error bars. So this is what we are passing to the model, the noisy measurement of the density profiles, not the actual intrinsic value of the measurement, the densities.
Okay, I had one more question, which is that early in one of your earlier plots where you show the regime within which, this one, feedback is important. What is the X on this axis?
So X is the distance, the normalized distance from the core of the dark matter halo. So this is the distance that is normalized by R200. So 0 corresponds to R200, -1 corresponds to 1/10 of R200.
Got it. Okay, thank you.
Thank you for your question.
Any other questions? We have time for maybe one more quick one. No? Okay, well, if anybody does want to discuss further, Arya has slots open on his meeting schedule, which you all should have gotten in your emails. I'll hand it over to Peter.
Thank you so much.
All right. Thank you for coming. Please welcome Dr. Alexandra Tetarenko. Dr. Tetarenko is currently a postdoctoral fellow at the James Clerk Maxwell Telescope in Hawaii. She completed her PhD in 2018 at the University of Alberta in Edmonton, Canada. Her research focuses on studying relativistic jets launched from stellar mass black hole systems in our galaxy, with a particular emphasis on observing these jets in the radio submillimeter regime. She's currently on the job market and actively looking for a new position to start in the fall of 2021. And she'll be speaking today about multi-wavelength fast timing and X-ray binaries.
Thanks very much. Can you guys all hear me okay?
Yes.
All right, so good morning, everyone. Today I'm going to be talking about a project that I've been working to develop for a couple years now, using time domain observations to study jet physics in X-ray binary systems, where I'm going to be focusing in particular on longer wavelength observations, so the radio and the submillimeter bands. And this work is done in collaboration with some of my favorite people listed here on the slide. All right, so before I get into all the cool science that we can do with the time domain, I want to first kind of briefly backtrack a bit and try and motivate why it's important to understand jet phenomenon in general and why X-ray binaries are the best way to do it. So determining how jets arise and quantifying the energy they carry are actually really important multifaceted problems in astronomy with implications for other fields of physics as well. For instance, jets have a fundamental effect on their environment, where injected energy can alter the chemistry of interstellar gas, in turn influencing large-scale processes such as the formation of stars and even the evolution of entire galaxies. Black holes and their outflows also provide unique laboratories to probe fundamental physics beyond Earth-based experiments. For example, in creating the first image of a black hole, the Event Horizon Telescope has performed some of the most stringent tests to date on general relativity. Additionally, jets also come into play within the new exciting areas of multi-messenger astrophysics. For instance, one of the most promising ultra-high energy neutrino candidates are actually the jets launched from supermassive black holes, as these jets can accelerate some incredibly energetic particles, which when they interact with radiation and matter can create exotic particles like neutrinos. So these jets are pretty much everywhere in our universe, and they're incredibly important for a lot of different astrophysical processes, but I will wholly admit that we still understand embarrassingly little about them, especially their fundamental properties. So our best chance to actually change this doesn't mean that we have to necessarily be studying the big supermassive black holes, like all the examples I just gave you on the last slide, because it turns out that smaller stellar mass black holes existing in X-ray binary systems in our galaxy are actually ideal test beds for jet phenomenon, because they're numerous, they're close to Earth, and they evolve on human timescales. And that's a really important one right there, because the majority of these systems are transient in nature, where they progress into these periods. They progress from periods of minimal activity into a bright outbursting state on timescales of days to months. And this means we can essentially watch them change in real time. And as you'll notice from the figure on the slide here, these objects are truly broadband objects, emitting all the way across the electromagnetic spectrum. So it kind of gives you a hint of how important multi-wavelength studies of these systems are, which I'll get into later in the talk. But of particular importance for today's talk is the jet emitting bands. That's going to be the longer wavelength, radio, submillimeter, and infrared. If you dig into the X-ray binary literature, more often than not, the kind of studies that you're going to find are going to be photometric studies or direct imaging studies with VLBI. But it turns out that time domain observations measuring how the intensity of the light we receive from these jets changes on different timescales essentially offers us a promising new way to address some of the key open questions in jet research. For example, we can probe physical size scales that aren't accessible with current imaging capabilities. If we, for example, if we pointed the Event Horizon Telescope at these systems, we still wouldn't be able to do as good in terms of size scales that we can probe as we can with a time domain. So the time domain essentially allows us to zoom in close to the black hole where these jets are launched. The time domain also allows us to probe notoriously difficult to measure quantities such as the energy output and the jet speed. And through comparing variability across different wave bands, we can also begin to link changes in the inflowing material with changes in the jet, thereby mapping out the sequence of events that leads to jet launching and particle acceleration like never before. So there's a lot we can learn from detecting variability in these systems, but to take full advantage of this, we need the right tools that allow us to both characterize what we see and connect variability properties between different wave bands. So one of the most useful tools that we have at our disposal is just a simple cross-correlation analysis. And this allows us to compare two time series signals. We can determine how correlated they are and estimate any kind of time lag or delay we might see in the emission between different bands. And this is incredibly useful because within an X-ray binary jet, higher electromagnetic frequencies are going to probe closer to the black hole, with the lower frequencies essentially appearing as a delayed version of these higher frequencies. So this delay, measuring this delay can actually allow us to get at the jet speed, which you will see later. Of course, beyond a cross-correlation analysis, if we go into the Fourier domain, we get some much more powerful tools because essentially we're adding another dimension to a cross-correlation analysis by going into the Fourier domain. We're able to measure lags, correlation behavior, variability amplitudes on many different timescales of variability. So we get much more information there. In order to use these really powerful tools, we of course need some solid software to do this. And I want to highlight one particular Python package called Stingray. And this package can do a bunch of different kind of timing analysis, and it's written by some brilliant X-ray astronomers who put basically all of their timing knowledge into this. And it's what I use for all of my timing analysis. So if you do this kind of science, I encourage you to check it out. All right, so given their incredible diagnostic potential, time domain studies have been used extensively to study the inflow of matter around black holes at X-ray wavelengths. But it's only recently that technological advancements have actually made it possible to do these time domain studies in the jet-dominated longer wavelength part of the electromagnetic spectrum. And while I told you that I'm going to be focusing on the radio and the submillimeter, the story didn't actually start there, because the first exciting advances in studying jet variability in X-ray binaries with these tools actually came in the optical and infrared. And this was due largely to the invent in the early 2000s of these new fast readout detectors, essentially allowing us to probe sub-second time resolution at the optical and infrared wavelengths, basically getting closer and closer to the capabilities that we had in the X-ray. And the first unambiguous detection of fast variability from one of these jets actually came in the system GX339-4, where we detected variability on sub-second timescales in the infrared, and we found that this infrared variability was highly correlated with the X-ray. And that's what you see on the left side of the slide here is a cross correlation function between the X-ray and infrared, showing about 100-second delay between the two. And this was really the first observational suggestion that variations in the accretion flow probed by the X-ray could actually be driving variability in the jet probed by the infrared in this study. And this is a really, so it was kind of like a really important proof of concept here. And this around 100 millisecond delay has been found in several other sources now, V44 SIG and MaxVJ1820, which I'm going to be talking about a bit later in the talk. Further, more recently, there's been some lovely work by Julian Malzak and his collaborators showing that we can actually reproduce these Fourier domain timing metrics that we see in the data with real jet models. And this opens up the possibility of actually being able to study detailed physical processes happening in the jet from just the analysis of variability. And that's incredibly, some really incredibly exciting work. Now, being a radio astronomer myself, when I first saw these studies, it made me wonder, well, what if we could do this in the radio in the submillimeter? What if we could actually track variability all the way from the X-ray all the way down the jet? Well, we've known for a while that radio jet emission is highly variable. And while the longer timescale variations have been tracked and well characterized in many systems, this is unfortunately not the case for the short timescale variations, less than a day, less than an hour, for which there's actually only been a handful of detections. And even in the case of these detections, little effort up until recently had been made to actually analyze this short timescale radio variability. For example, one of the very few radio frequency Fourier domain studies that exist out there was from Nepoti et al. Way back in 2005, where the longest timescales probe, or the shortest timescales probe, sorry, were days. And the main reason for this sort of lack of study in this area is that while time-resolved observations are a staple for X-ray binary studies at X-ray and even optical and infrared wave bands right now, there are many extra challenges that we face trying to do this in the radio and the submillimeter. In particular, it can be difficult to disentangle intrinsic source variations from atmospheric or telescope gain variations. Observations often involve routinely cycling between a target source and a calibrator. And in most cases, you can only observe one frequency band at once. So all these obstacles prevent continuous observations of the jet, can introduce artificial periodic signals into the data, all of which can complicate the time domain analysis. And up until recently, most of our telescopes weren't even sensitive enough nor capable of taking rapid second to sub-second data in these wave bands as well. And lastly, when we look in the radio, say you take a telescope like the VLA, sure, you have this big archive of past observations, but all the observations in there are usually short, single frequency observations separated by days. So we can't even really go back into the archive to get old data to try and understand this variability. It's not like, for example, in the X-ray where you have a beautiful archive like something from RXT. So I painted kind of a bit of a bleak picture, but it turns out that with today's more sensitive interferometric arrays, which offer a lot of more customizable and flexible observing modes, we can actually begin to start lifting some of the limitations that I just talked about and begin to sample these jets at radio frequencies in the time domain. But unlike, for example, in optical and infrared, where having a better instrument really kickstarted these timing studies, just the better instrument isn't enough in the radio. Because of the extra limitations that we face, we have to get super creative with how we're using this instrument. So one of the techniques that's proved to be incredibly important in overcoming some of these limitations with radio timing is what we call the use of subarrays. So if we have a large interferometric array, again, like the VLA, what we can do is we can actually separate it into individual subarrays that basically operate independently of each other. So you can imagine, for example, observing a different frequency band with each subarray, and then you've just solved the simultaneous multi-band problem. And we did this quite successfully first with during the 2015 outburst of V44 Cygni, and that's what you see here on the left side. of the slide with some beautiful light curves that we got of this system, where we have 4 different frequencies using a subarray VLA combined with some submillimeter data from the SMA and JCMT. So this was, and we were able to produce these really beautiful simultaneous light curves of some incredible flaring activity that happened in this system. And a bit of a fun fact on subarrays, if you dig into the literature, it turns out that Felix Mirabel and his collaborators actually attempted to use subarrays on GRS 1915 plus 105 back in the late 90s. So he actually gets the credit for this technique. Now, what we were able to do with B4 for SIG was really great, but we were a bit more ambitious. You can imagine, for example, using your trying to actually sync up your subarrays to get longer bouts of continuous data. For example, you can sync them up so that one of them is on a calibrator, these are the others on the target, and you get this longer bouts of continuous data. And this is important because it gives us access into the Fourier domain, and you've seen in the OIR studies how important that was for characterizing the variability. So our attempt to use this synced up subarrays, we actually did a bit of a pilot study on Cygnus X1, where we combined subarray VLA with NuStar in the X-ray. And that's what you see on the slide here, X-ray light curves on the left, radio on the right. And what we end up actually finding is that the radio signals we were observing showed some clear structure variability, as you can see pointed out with the arrows on the slide, in terms of some small scale flaring events. And the radio emission was also varying significantly down to about tens of second timescales. By comparing the radio and the X-ray, we actually also found that the emission was highly correlated, not just between the radio bands, but between the radio and the X-ray. So using cross-correlation functions, we find clear delays between all these different bands of about tens of minutes between the radio and X-ray. And through mapping out these lags, like you see on the bottom of the slide here, we observe a clear trend with electromagnetic frequency. You know, the lower frequency bands probing further out of the jet are always lagging the higher frequency bands. And this is consistent with these lags actually presumably tracing the propagation of material downstream along the jet flow. Now, finding lags like this in X-ray binaries isn't a new thing, but what is measuring lags to multiple different bands at once. And this is important because once we have these multiple lags, what we can do is we can actually model the lags and we can get a direct measure of the jet speed out. And this is exactly what we did here for the first time in X-ray binaries. And we found that this jet was actually moving quite quickly, about a bulk length factor of 3. So this study ended up being not just successful observationally in terms of proving that, you know, radio timing is actually possible. We can also see that we've begun to start to actually pull out some real physics from these time domain observations. But once again, you know, we were still a little bit more ambitious. So we thought, how can we make these studies better? Well, we need to add more frequency bands, more simultaneous bands to probe a larger portion of the jet. And this is what we ended up doing in March 2018 during an outburst of a system called MAXI J1820 plus 070. So this system was first discovered as an optical transient by Assassin and has since been a dynamically confirmed black hole system. And it's really a perfect target for these timing studies because right now we have a parallax distance to this object. This thing was incredibly bright. We're talking hundreds of millijanskys in the radio. And we already knew that it was highly variable in the X-ray and the optical. So that suggested that we were going to see some fireworks in the radio and submillimeter as well. So what we did was we combined subarray VLA again with ALMA this time, and we get this killer combination, and we see some incredible variability in these light curves, ALMA on the left and VLA in different bands on the right. So you can see we see this really rapid flaring across all of our different bands. And in order to actually characterize the variability we're seeing, we start with the Fourier domain. And we make some power spectra of our emission. That's what you see on the right side of the slide here. And you'll notice that all the power spectra show a kind of broken power law type shape, where the highest power occurs at the lowest Fourier frequencies, corresponding to the longest time scale sampled. However, there are clear differences between the power spectra for the different wave bands. Well, you'll notice that the higher electromagnetic frequency bands, so ALMA, that's in the green, tend to show higher peak variability amplitudes, and you can almost see that the break in these power spectra moves to lower Fourier frequencies as we shift to the lower electromagnetic frequency bands. And this is the first time that we've actually seen an evolving power spectra with electromagnetic frequency in black or actually binaries. And it was incredibly exciting because this is something we've been looking for from the beginning. And the reason for that is if you look on the left side of the slide, this is exactly what we predict from some new jet models, in particular Julian Malzak's internal shock model. You see he also predicts this evolution in the shape of the power spectra. So to kind of put more of a quantitative spin on this evolution that we're seeing, what you see here on the slide are measurements of the Fourier break frequency and as well integrated fractional RMS under the power spectra. So you'll notice we pull out again these beautiful trends with electromagnetic frequency bands. And one of my colleagues actually came up with a really good analogy to essentially what we're doing here. So we believe that the Fourier frequency break is at least to first order tracing the downstream distance to the emitting regions in the jet. So my colleague suggested that it was like almost like we were using the black hole as radar or sonar, mapping out the structure of the jet for the first time, which is quite cool. Similar to our early SIGX-1 study, we also did some cross-correlation analysis to look for lags as well. And we found these lags again between the radio bands and the radio and the submillimeter, where we're getting on the order of minutes between these bands. And again, we see the same kind of trends where, you know, lower frequencies are always lagging the higher frequencies. So essentially what we've done here is we have a bunch of different timing characteristics that we've measured. All right, so we have the average spectrum, we have the Fourier break frequencies, and we have a bunch of lags. So the question is, how do we actually make a connection to some real physics here? Well, it turns out all these different quantities can be predicted by a classic kind of Blandford-Condrel jet model. But the problem is that if you try and measure any one data dimension or model any one data dimension at once, your model is highly degenerate. It turns out though that if we simultaneously fit all these different data dimensions, add in the fact that we have independent constraints on distance and inclination, we can actually overcome these degeneracies. And this is exactly what we've done. We've been able to simultaneously model all of our data here, and that's what you see on the slide. And what ends up coming out of our best fit model is we find that this jet is highly relativistic, so even faster than the SIGX-1 jet, closer to around a bulk Lorentz factor of 4. It's highly confined, and it's actually carrying a significant amount of power, almost about 10% of the bolometric X-ray luminosity at the time. So the bottom line here is we've developed a way to actually derive fundamental jet properties from light curves alone. And this is an incredibly powerful tool. So where do we go from here? Well, we've laid the groundwork for these new time domain tools, but now what we need to do is we need to expand these studies to address some of the major shortcomings that we still have in this current framework of spectral timing experiments. In particular, the majority of these studies are all still one-shot observations. So we're unable to probe how these jets evolve throughout different stages of their outbursts. You know, everything that I've showed you today has only been these one-time observations. For example, if we take a look on the slide here, this is essentially the observational coverage that we had of MAXI J1820 during its outburst in the radio and submillimeter. So you'll notice that it's quite sparse. And only one of these observations was actually enabled to do radio timing. Now, imagine if our coverage instead looked like this. We had 16 different timing-enabled observations throughout an entire 300-day outburst. We could actually be able to do the same thing. We could be measuring fundamental jet properties in each of these observations and actually be able to track how they change throughout an outburst. The second sort of shortcoming that we face is the studies focusing on longer wavelengths have still remained largely separate from those focusing on shorter wavelengths. And this means that we're unable to connect variability across different regions in the inflowing material and the jet. So in the same way I've presented them in this talk, you know, the optical and infrared were separate from the radio in some millimeter. So we really need to change that. And lastly, the third shortcoming is that all the studies that we've done so far have only focused on the total intensity component of the jet emission. So there's been little exploration of how a polarized components of the jet emission can actually change on different time scales, especially in sub-millimeter wave bands, which are free of some contaminating external effects, for example, Faraday rotation, which ends up being quite a complication in the radio. So how do we actually address all these shortcomings that still exist in these spectral timing studies? Well, I developed a multi-year large observing program that we call Pitch Black. It stands for Polarization and Timing Characteristics in Black Hole Jets. And what it does is it connects a global network of telescopes anchored by a large program on the James Clerk Maxwell telescope here in Hawaii. And this program is designed to do a systematic time domain study of 6 stellar mass black hole outbursts over the next 3 years, where we're going to be simultaneously observing systems across a range of timescales and wavelengths, including this vital sub-millimeter polarization component. The idea is we're going to build up a large uniformly sampled set of these X-ray binary observations, and this is really what's going to allow us to move beyond single source studies, connect the wavelengths, and actually explore sub-millimeter polarization for the first time. And we hope that this large data set will allow us to start to begin to answer some of the open questions in jet research, especially really putting solid constraints on fundamental jet properties. All right, so hopefully I've convinced you today that time domain analysis is an incredibly powerful tool with which to study accretion and jet physics, near compact objects. And we're not just limited to the X-ray bands anymore. You know, we can do this in the radio, we can do this in sub-millimeter, we can do this in the infrared. And the studies that I've shown you today have shown that, you know, we aren't just capable of doing these studies now, we can actually start to pull out fundamental jet properties from just time domain measurements alone. And while the stuff I've shown you is, you know, showing some early successes in these spectral timing experiments, they still are very much in their infancy. So we need to continue to improve and adapt them. And in particular, looking towards the future, what's really exciting is the improved capabilities of some next generation instruments. If we think about like NGVLA, ALMA 2030, SKA, they're going to play a key role in this science in terms of increased sensitivity and wavelength coverage. So there's a lot of exciting prospects for continuing to develop these spectral timing experiments. And I really believe that they're going to be key in driving some new discoveries in X-ray binary field in the coming years. And lastly, just to finish off, a bit of shameless self-promotion. My current fellowship is ending next year, so I am on the job market. And if you know of anything, I would very much appreciate a heads up. Thank you.
All right, thanks, Alex, for a really neat talk. We have time for 1 or 2 questions. If you could raise your hand or send a message either in the chat or Rutu's monitoring the Slack channel. Also, Alex has a sign-up sheet for Zoom meetings afterwards in the spreadsheet that was mailed about. Any questions?
Hi, this is Steve Wellner. I don't have, I can't figure out how to raise my hand.
That's fine, you're the first.
I'm wondering, this is a great talk. I don't work in this field and I really like the talk, but I'm wondering if you could just say a few words about the physical model that you're proposing. Is it that some electrons are injected and then they're accelerated down the jet, or are they decelerated, and what are the magnetic fields like, and just an overview of that?
Yeah, for sure. So what we're using right now to model our timing properties is just a classic kind of Blandford-Condrel jet model. So it's just, as you said, we have we have a population of electrons that's accelerated up into a power law energy distribution and down the jet. But beyond this kind of model, what's also sort of very interesting in terms of modeling timing properties is actually, I mentioned a couple times briefly, is Julian Malzak has this new internal shock jet model where essentially the jet is composed of a series of shells injected with different velocities, where the fastest kind of fluctuations catch up with the slower ones and merge to actually produce these internal shocks. And that's the idea of what's actually driving the variability, these kind of small scale flaring events that we're actually seeing in the light curves. So right now that's sort of a next step for us, is being able to actually try and see if we can use that model to predict a bit more about what we're seeing in the timing properties. But yeah, that's another interesting jet model that we want to get into and try and compare to our measurements as well.
Okay, thanks.
Any other questions? All right, well, if not, thank you, Alex, and thank you all for coming.